today's keynote speaker, Professor Dr. Aryam Dhaigude sir, and resource person, Professor Dr. Amol Sonone sir, to give us important guidance. Before that, I request our chairperson, respected principal, Dr. Shivdas Shirsat sir, to give us some guidance. Sir,
Good morning, everybody. Today, I am very happy to inaugurate the one-day national level seminar on reaction diffusion theory organized by Department of Mathematics. I am grateful to Honorable MLA Shri Prakasada Solanki, President Marathwada Shikshan Prasarak Mandal, and Honorable MLC Shri Satish Bhau Chavan, General Secretary Marathwada Shikshan Prasarak Mandal, Chhatrapati Sambhajinagar. Our CDC members, Honorable Dattatreya Abba Patil, Dr. Narendra Jikade, and Honorable all CDC members. The office bearers of all organizations have given their best wishes for this seminar. Today, our guest of honor and keynote address of this seminar, Honorable Professor Dr. R.M. Dhaigude sir, Department of Mathematics, Government Vidarbha Institute of Science and Humanities, Amravati. Resource persons, Professor Dr. Amol Sonone, Department of Mathematics, Government College of Arts and Science, Chhatrapati Sambhajinagar. My colleague, Vice Principal Professor Ramesh Shinde and Professor Swapnil Aunde, Organizing Committee Convener Dr. Professor Megharani Patil and Professor Naveen Chauhan, Science Faculty Coordinator Dr. Arvind Ghodke, our IQAC coordinator, Dr. Mukund Rajpankhe, and co-coordinator, Dr. Ahilya Barure, who played a vital role in organizing this seminar and technical support. I have an immense pleasure to organize these events for the benefit of new beginning scientists, research scholars, and faculty. Dear participants, the aim of this seminar is to introduce reaction diffusion theory. There are non-equilibrium systems of diffusing classical particles which undergo reaction such as pairwise annihilation. Reaction diffusion theory describes how chemical reaction and diffusion process can lead to the information of stable self-organized pattern such as spot, strips, or spheres in various systems. This theory, often attributed to Alan Turing, suggests that this pattern arises from the interplay of chemical reaction and the movement of molecules through a medium. Reaction diffusion theory provides a framework for understanding how complex pattern can arise from simple chemical interaction and diffusion process. It has implications for various fields, including developmental biology, material science, and synthetic biology. Lastly, I appeal to the participant to be online throughout these events and take the benefit of the deliberations from experts. I hope that there will be fruitful discussion in this seminar. Thank you once again, one and all. Jai Hind, Jai Bharat.
thank you, sir. It's really proud and honor for our college to organize such a beautiful program with us amazing guest, keynote person. Professor Dr. R.M. Dhaigude sir, and resource person Dr. Amol Sonone sir. Words are too short to describe their achievements. Then I request my colleague Chavan sir to introduce our today's honorable respected guest, Dr. Dhaigude sir. Chavan sir.
Thank you. Thank you, madam. My regards to everyone. Marathwada Shikshan Prasarak Mandals, Yeshwantrao Chappan College, Ambazobai has organized a one-day national seminar has today, and I take this opportunity to introduce the keynote speaker who has been invited for the seminar. Dr. Aryam Dhaigude sir is MSc, MPhil and PhD. Honorable sir is currently working as a professor in the Department of Mathematics at Government Vidarbha Institute of Science and Humanities. He has 24 years of experience in teaching mathematics. He has made a great contribution in research and has been working in the field of research continuously from last 15 years. He has published 39 research papers in the national and international journals. Till this date, he has presented 6 research papers in national and international conference too. He is a research guide and his 4 scholars have obtained their PhD degrees under his Nobel guidance. He has 2 books to his credit. He is a life member of Indian Mathematical Society and is also a member of Marathwada Mathematical Society. He has also been honored with various awards for his remarkable work, including Mahatma Phule and Dr. Babasaheb Ambedkar Research Award 2015, Outstanding NSS Program Officer Award 2010, presented by Dr. Babasaheb Ambedkar University, Chhatrapati Sambhajinagar. On behalf of the college, I extend a warm welcome to such a great person in the field of mathematics as the keynote speaker for today's seminar. I hand over the responsibility hereafter to the program coordinator. Thank you.
Thank you so much, sir. To know the more about today's topic, organized by our college and Department of Mathematics, I like to invite Professor Dr. Aryam Dhaigude sir to deliver speech on reaction diffusion theory. Sir.
Thank you, madam. Firstly, I thankful to Principal Dr. Shivdas Sirsat sir, Shinde sir, and other faculty members, because I give the good opportunity to present the keynote address. So, without spending more time, I will start my research presentation, which is beneficial to the research scholars and so many research students also. One minute. स्क्रीन विजिबल आहे ना सर्वांना? हॅलो.
Yes, sir. Yes.
Okay. Now we introduce the reaction diffusion theory, types of reaction diffusion equations, some important reaction diffusion equations, and some applications of reaction diffusion equations, existing methods of solving reaction diffusion equations. Now, in a chemical systems which are not well mixed, we have to take into account of the fact that chemicals move through space due to diffusion. We begin these notes with short account of the laws of diffusion. The fundamental quantity in the study of diffusion is a flux, that is the amount of chemical which passes near a point in space per unit area per unit time. Thus, reaction diffusion process are the mathematical models which corresponds to different physical phenomena in the applied sciences. Space and time cannot be considered as independent variables in this equation. An equation of the reaction diffusion contains terms of reaction and terms of diffusion. Models of reaction diffusion are widely used in the field of chemistry, physics, and engineering sciences. However, the model can also represent non-chemical dynamic process. What happens if we have reaction and diffusion? It turns out the net effect of these two processes is just the sum of the individual rates of change. Thus, if a reaction or set of reactions leads to reaction rate terms R, then we get this equation dou C by dou T is equal to d del square C plus R. For obvious reasons, this is called a reaction diffusion equation. Reaction diffusion equations are the member of more general class that is known as a partial differential equations because they involve the partial derivatives of functions of many variables. In the case of reaction diffusion equation, that C depends on T on the spatial variables. To fully specify a reaction diffusion problem, we need the differential equations with some initial conditions and boundary conditions. And the initial conditions will be initial values of the concentrations over the domain of the problem. And the boundary conditions are the new elements. In general, there will be special conditions at the boundary of the domain such that the differential equation does not apply there. Mathematically, the reaction diffusion systems take the form of semi-parabolic partial differential equations, and they may be described as follows in the general form, which is they are described. Some research is by the Labroda in 2017, and these are the equations. Dou S of at point xt by dou t is equal to ds del square s of st minus f of st. And at point p, there is only change, that is plus g of sp in this equation, where that s of xt is a substrate and p of xt is a product that represents unknown vector function. And where capital D is
हॅलो
the diffusion coefficients.
धायगुडे सर
Ha, sir.
स्लाइड फक्त पहिली दिसते सर, नेक्स्ट स्लाइड्स दिसत नाहीत.
कसं काय गडी? एक मिनिट सर. एक मिनिट हा. काय प्रॉब्लेम केला सर?
आता चेंज झाली सर.
एक मिनिट बघू, करतोय प्रयत्न. आता दिसते का सर?
येस सर,
हॅलो.
येस. हो.
दिसते ना सर? चेंज झालेले दिसतायत ना?
हो सर,
हा,
हो, चेंज
दिसते
झाली.
सर.
करंट स्लाइड दिसते.
अच्छा, इक्वेशन 2 आणि 3 दिसतायत ना?
हो सर, हो.
हा, ओके सर. In this equation, where S of xt substrate and P of xt is a product represents the unknown vector function, and where capital D is the diffusion coefficients, and F of sp and G of sp are the accounts for all local reactions. This is a linear or non-linear function. This function depends upon the type and nature or order of the reactions. The first term on the right hand is called diffusion term, and the second term is called reaction term. And del square is the Laplace operator. Now we'll see the types of reaction diffusion equations. Basically, there are two types of reaction diffusion equations depending on the nature of reactions term, where linear reaction diffusion equations and non-linear reaction diffusion equations. Linear reaction diffusion equations describes systems where reactions and diffusions processes are proportional to the concentration or other relevant variables. The simplest form of linear reaction diffusion equation is given by the equation first, which we have seen, in which where R is equal to R of C is a linear function of the concentration C. These equations can model heat diffusion, population dynamics with simple growth and decay, or the spread of substance in a medium. On the other hand, nonlinear reaction diffusion equations involves terms where the reaction or diffusion rates depends non-linearly on the variables. That is, these equations involves terms like C square or C cube, that is non-linear in the concentration C, often leading to more complex and interesting behavior. These equations are used to model various phenomena in biology, chemistry, and physics, where spatially inhomogeneous processes are common. That is a population dynamics model with competition, prediction, or density dependent growth. And chemical reactions rates depends on multiple factors or the product of reactants. And phase transitions, the rate of change of materials state depends on nonlinear factors. Finding a solution of such equations can be significantly more difficult and more often requires numerical methods. Now, some important nonlinear reaction diffusion equations. Furthermore, the nonlinear reaction diffusion equations are classified into 5 types depending on the nature of boundary conditions. The variable x is often confined to a domain omega with boundary dou omega, and then solutions are sought which satisfy the specific initial and boundary conditions on dou omega, that is the boundary of the domain. Boundary conditions are those which depends on space. चेंज नाही होत का? प्रॉब्लेम काय आहे? एक मिनिट सर, चेंज होत नाही म्हणते. कनेक्शनचा कसं काय प्रॉब्लेम? एक मिनिट, चेंज होत नाही असं हे झालं. एक मिनिट हे करतो मी. हेच राहू पहिली काढणार ती दिसते ना स्लाइड. Some important nonlinear reaction diffusion equations. In this article, we have seen the variable x is often confined to domain omega with boundary to omega, and then solutions are sought which satisfy specific initial and boundary conditions on do omega. Boundary conditions are those which depends on space, while the initial condition depends on time. Generally, the boundary conditions have the following types. There are 5 types of boundary conditions, that is Dirichlet, Neumann, Robin, mixed, and Cauchy, within which Dirichlet and Neumann are predominant. In the table below, अगोदरची स्लाइड कोणती ती? आता ही होत नाही पुढे. अच्छा, ही का? In the table below, L, M, alpha, beta, Fg are the known as a scalar functions, and ds by dn is a directional normal derivative. S and P are unknown functions. These are the boundary conditions, that is a Dirichlet boundary condition, Neumann boundary condition, Robin boundary condition, mixed boundary condition, and Cauchy boundary condition. Now we see some applications of reaction diffusion equations. Nonlinear diffusion has been the most powerful tool for mathematical modeling of various processes in biology, geology, and physics. Neutron diffusion theory is introduced the topic, and medicine, physiology, diseases, all these, genetics, social sciences, finance, economics, whether the prediction, astrophysics, and ecology also. Pioneering models have been developed to describe some of the classical laws in physics and astronomy. Here we will discuss some of them as follows. Now, in biological sciences, nonlinear differential equations describe the different biological process such as population dynamics, gene propagation, environmental inhibitions, predictor pre-equations, and dynamics of competitions. In biological sciences, the notorious nonlinear equation is the Burger's equation and the Fisher's equation. Now, in physical sciences, nonlinear differential equations occur in several fields of physical sciences. For instance, in particle physics, plasma physics, charged nanoparticles, image processes, fluid mechanics, soliton physics, quantum field theory. The relevant examples are the Riccati equation and Poisson's-Boltzmann equations. Now, in chemical sciences, nonlinear reaction diffusion equations is utilized in organic and organometallic processes, homogeneous mediated enzyme catalyzed reactions, multi-layered enzyme modified electrodes, and nanostructured porous film, polymer modified ultramicro electrodes, biosensors, biofuels, cells, and bioreactors. And nonlinear reaction diffusions equations are naturally implemented in physical and electrochemistry. And this equation is obtained by combining Fick's diffusion law with the law of chemical reactions rate. Reaction diffusion equations are also in medical sciences. Mathematical models are also used to describe biomedical processes. All the models are based on nonlinear partial differential equations, and usually they are not linearizable. Nonlinear differential equations occur in different pharmaceutical science fields such as infectious disease, cancer, growth, and blood coating, distribution of heat sources in human body, nerve plus transmission and neurosciences. An epidemic is a sudden spread of the disease in a given population to large number of people within limited period. Example, cholera, SARS, malaria, plague, and corona. COVID-19 is a new model, not SEIR, and other models. We scientists searched this in 2020. This system is based on the nonlinear rate equations of substitutable, uncovered, curable, affected genital infections, infected and removed people, including recovered and dead people, containing nonlinear terms related to the transmission period. Infections period, transmissions rate, and death rate, the lifetime of viruses, all these. And in engineering sciences, in many applied sciences such as a heat transfer, soil consolidation, electricity, quantum mechanics, water flow, thermodynamics, concentrate, carbonation, classical and fluid mechanics, solid mechanics, and other. The problems are overseen by nonlinear partial differential equations. And Euler-Bernoulli beam equation is one of the essential examples of linear equations in engineering sciences. The coupled nonlinear equations of motion in have role and pitch are based on physical grounds in ship dynamics. The materials for design and implementations are composed of three components. These are friction forces and moments, the regeneration of forces and moments, and the damping of forces and moments. Now, existing methods for solving reaction diffusion equations. The well-known linear superposition principle cannot be applied to generate new exact solutions for nonlinear partial differential equations. This implies that classical methods, that is the Fourier methods, the Laplace transformation methods, and the green functions, are not helping to solve these partial differential equations. Thus, constructing unique exact solutions for these equations is a non-trivial problem, but it is of the fundamental importance to find accurate or approximate solutions which have a physical, chemical, or a biological interpretation. The approximate solutions for strongly nonlinear differential equations depend on one-dimensional, multidimensional, steady state or non-steady state, migration effects, system of ordinary differential equation or partial differential equations, coupled by the homogeneous kinetics, heterogeneous kinetics terms, and hydrodynamics related to fast or slow diffusion. Over the last few decades, different methods have been reported to obtain the analytical solutions such as extended tanh, Jacobi elliptic function, expansion, and sine cosine methods. Some of the powerful analytical methods which are applied to solve the nonlinear problems recently are listed with mere introduction in the upcoming slides. Now, homotopy perturbation method. In this method, the homotopy perturbation method is an effective and useful method for finding solutions to nonlinear equations. This method was first introduced by He in 1998, then 1999. The combination of the perturbation method and the homotopy method is called HPM, which eliminates the disadvantages of traditional methods of perturbation while retaining all its advantages. Now, homotopy analysis method. The homotopy analysis method is a semi-analytical procedure used to move nonlinear differential equations. The HAM was first developed by Leo of Shanghai Georgetown University in this PhD thesis in 1992, and further modified 1999 to introduce a non-zero auxiliary parameter in 1997. The convergence control parameter is a non-physical variable that provides an easy way to check and implement the convergence of series of solutions. Then a domain decomposition method. In 1923 to 1996, George Odmian developed an influential approach to unswearing nonlinear equations in 1980. The method is called a domain decomposition method. The technique is based upon functional equation representation as a series of functions. Every term in the series is obtained from a polynomial generated by an expansion of the power series. Variational iteration method. This method is developed in 1999 by He and also 2006 by Hu, will be used to analyze the nonlinear or linear wave equation and wave-like equation in bounded and unbounded domain. The variational iteration method has been familiar semi-analytical method for finding the solutions of nonlinear partial differential equations. The most significant advantage of the approach is its simplicity and ability to solve nonlinear equations rapidly. By this method, if such a solution exists, one can find the successive convergent approximations to the exact solution of the differential equations. Exponential function method. He and Wu in 2006, he find this method and first suggested this approach and were successfully applied to obtain the solitary and periodic solutions of partial nonlinear differential equations. Furthermore, several researchers used this approach to handle various other problems such as stochastic equations or also stochastic differential equations, a system of partial differential equations, high dimensional nonlinear evolution equations in 2008, and differential equation Bikir 2010, and long wave nonlinear disparative equations, that is in 2009. Now, hyperbolic function method. This method was first proposed by Devi in 2020, or Rajendran. This is a recent research of the reaction diffusion theory, and was successfully applied to obtain the approximate analytical solutions of nonlinear differential equations. Hyperbolic function method is a special case of an exponential function method. Further, this method was used by many researchers for handling various nonlinear differential equations. Now, variational factoral theory. The most interesting features of the variational factoral theory method are its extreme simplicity and consists forms of variational functions for a wide range of nonlinear problems. Now, Taylor series and Pade approximation method. In this Taylor series is a description of a function as an infinite number of terms determined at single point from the value of the function's derivatives. This subject was first formulated by the Scottish mathematician James George and formally introduced by the English mathematician Brooke Taylor in 1715. If the Taylor series is centered at zero, then that series is also called Maclaurin series. After the Scottish mathematician who made extensive use of this special case of Taylor series in the 18th century. Pade approximation, the Pade approximations are the special type of rational approximation. This technique was invented by Henry Pade around 1890, but goes back to George Frobenius, who introduced the concept and characteristics of rational approximations. The Pade approximations also gives the function a better estimate than transcutting its Taylor series, and it can be also operate where the Taylor series does not converge. Pade approximations are widely used in computer calculations for these purposes. Next method is parametric expanding methods. This method is searched in 2000 and also by 1999. Now this is the also recent research in the reaction diffusion theory. This method is applied a parameterized permutation method to find approximate solutions for nonlinear differential difference equations. Simply, but traditional examples are used to uh, demonstrate the validity of the process and its great prospective. The highly accurate results reveal that the technique is beneficial and straightforward. Now we'll see some these are the some references of this topic. Okay, thank you. Uh, Thank you, sir. Have you any questions? Can discuss with me, no problem. This is a new research of the reaction diffusion theory. Hello. Hello, Shirsat sir. आवाज जातो का नव्हता?
Patil madam.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Okay, thank you, madam. Thank you.
Your information and valuable guidance. It will be very beneficial for all our students and we also.
मॅडम
Then
तुमचा
I-
व्हिडिओ असं आडवा दिसतोय. हा ओके मॅडम. हा आता ठीक आहे. हो
दिसते का सर व्यवस्थित?
हो मॅडम. हो.
दिसते.
Then I again to request Jadhav ma'am to introduce our next resource person, Dr. Amol Sonone sir. Jadhav ma'am.
Thank you, ma'am. My regards to everyone. I take this opportunity to introduce the resource person who has been invited for this seminar. Dr. Amol Sonone, sir, MSc, SET, NET, PhD. Honorable Sir is currently working as an assistant professor in the Department of Mathematics at Maharashtra's Government College of Arts and Science, Chhatrapati Sambhajinagar. He has 14 years of experience in teaching mathematics. He has made a great contribution in research and has been working in the field of research continuously from 7 years. His research interest is in graph theory. He has published 7 research papers in national and international research journals till this date. He has presented 3+ research paper in national conferences too. He attended 3+ workshops also. He has been honored with various awards for his remarkable work, including Gold Medal awarded by Savitribai Phule Pune University for the best PhD thesis in mathematics for the year 22-23. Best Paper Representation Award at International Conference on Discrete Mathematics held at Sundarnar University, Tamil Nadu. Best Paper Presentation Award at International Conference on Discrete Mathematics held at the Department of Mathematics, Savitribai Phule University, Pune and COEP Technological University, Pune. On behalf of this college, I extend a warm welcome to such a great person in field of mathematics as a resource person for today's seminar. I hand over the responsibility hereafter to the program coordinator. Thank you.
Thank you. Thank you, ma'am. Now I will request to the Honorable Dr. Sonone sir to share his knowledge with us about today's topic, reaction diffusion theory. Sonone sir.
Am I audible, madam?
Yes, yes, sir.
Thank you, madam, for the nice introduction. Respected Daigude sir has presented a nice presentation on the topic, the reaction diffusion theory. After that, I have decided to change the topic, that is decomposition of graph. It is sort of related to diffusion means decomposition, but I have just in point of students and teaching faculties related to computer science and mathematics, I have just decided to change the topic decomposition of graphs. Okay. See, all mathematics students and almost all teachers of mathematics know the graph. What is meant by graph, right? So graph, we study graph in graph theory. But what is graph theory? Graph theory is just a branch of discrete mathematics, has a wide range of applications in real life scenarios like interconnection networks, transportation flow problems, computer science, electrical engineering, designing of circuit connections in electrical engineering, operations research, and chemical graph theory. Let's see the what is definition of graph. See, graph, generally we denote graph by
हॅलो सर, आवाज येत नाहीये. हॅलो. हॅलो सर. हॅलो सर. आवाज.
मॅडम कॉन्टॅक्ट करा त्यांना.
सर सोनवणे सर. नाही त्यांचा नंबर. सोनवणे सर. हा. मग त्यांचा विचारून सांगत होते.
मॅडम सर रिजॉईन होत आहेत 2 मिनिटांमध्ये.
ओके ओके सर. रिजॉईन नाही. फोन लावायचा होता.
हॅलो, आता
हा
येते
सर.
मॅडम.
हा यस यस.
Is my screen visible?
Yes, yes, sir.
Sorry for the technical glitch. See, we were seeing the definition of graph, right? I'm starting from here again. A graph is a pair of V and E, where V is the set elements are called vertices and or points or nodes, and E is a set of paired vertices whose elements are called edges, lines, or links. Right? See, just recall what are the graphs we studied in the graph theory, which are generally standard graphs are cycles, paths, trees, stars, complete graphs, complete bipartite graphs, and null graphs, and etc. We studied a lot of types of graphs. Just let's there is one software that is graph-t. Let's we generate the graphs for just recalling. See, we know the standard graphs. Suppose a cycle. What is cycle? See, we know that a cycle is a graph, connected graph. such that degree of each vertex is 2. See, this is cycle. Cycle means suppose we start from one vertex, we goes to another vertex, then next vertex, then again next vertex, then again come to the uh, starting vertex. This graph is called a cycle. Let's generate another cycle. Suppose whose vertices, number of vertices are 5. See, this is a cycle with 5 vertices, right? Similarly, using this graph T software, we can generate many more graphs. See, for example, let's generate another cycle with 6 vertices. See, this is cycle with 6 vertices, right? Okay. See, we also studied what is mean by path. See, path. Path is nothing but a connected graph in which exactly 2 vertices of degree 1 and remaining vertices have degree 2. See, let's see what is path. Let's generate a path with suppose 7 vertices. See, this graph is called a path. See, means just like a way. Means we start with one vertex and we
Hello, sir. You are not audible. Sir, not audible. आवाज येत नाही. सोनवणे सर. सर,
सोनवणे सर. हॅलो, सोनवणे सर.
सोनवणे सरांचा आवाज येत नाहीये.
सोनवणे सर, आपला आवाज येत नाही.
नाही येत सर. तांत्रिक अडचण आहे. आली सर. सर डबल जॉईन होत आहेत.
ठीक आहे मॅडम.
हॅलो हॅलो, येतोय का आवाज होता? हॅलो
हो सर, हो सर.
हॅलो. हॅलो, येतोय का आवाज आता?
हो सर, येतोय आवाज.
ओके ओके. मी आता लॅपटॉप पण जॉईन केलंय. See, sorry again. Let's start with where we are. See, the graph, we have seen the graph is a order pair in which we the set of vertices and is a set of edges, and we are just generated the standard graphs using graph software. See, we know the chromatic number of the graphs. The chromatic number of a graph means minimum number of colors need to color all the vertices of the graph such that any two adjacent vertices must have different colors. See, we know that the chromatic number of a cycle with even number of vertices is always 2, because we can color the vertices of that cycle having even number of vertices alternatively with different colors, and we require at least 2 colors. So the chromatic number of cycle is 2. And the similar and if we take a cycle with odd number of vertices, then we know that we require at least 3 colors. So the chromatic number of the cycle having, hello, slide share नाही झालेली का? Okay, just a minute. Just a minute. Screen दिसते का मॅडम? हॅलो.
Yes, yes, sir. Yes. Yes, and notes.
See, just we have discussed the chromatic number of a graph, right? And see, if we see the graph, class of all graphs whose chromatic number is 2, then we can conclude that a graph is bipartite if and only if its chromatic number is 2. See, let's see another definition which is important. Connected graph. A graph is said to be connected if there is a path between every pair of vertices. Means if we can able to reach from any vertex to any other vertex of the graph, then that graph we have to call as a connected graph. And if suppose there exist two vertices, we cannot reach from one vertex from the other vertex, then the graph is called as disconnected graph. Means we can see the parts of the graph different at different places, so we cannot reach from one place to another place. Such graph we call a disconnected graph, right? And the connectivity of the complete graph. Complete graph means a graph in which any two vertices are adjacent is called a complete graph. And we know that the connectivity of the complete graph with n vertices is always n minus 1. And connectivity of non-complete graph is the minimum number of vertices that need to be removed from the non-complete graph such that the resultant graph is disconnected graph. Means the minimum number of vertices need to remove from the graph to get this resultant graph as a disconnected graph is called the connectivity. With that minimum number of vertices, we call the connectivity of that graph, right? And see, we know the connectivity of the standard graphs. The connectivity of cycle is always 2. The connectivity of path is 1, right? Because if we remove any middle vertex, then the resultant graph becomes disconnected. So the connectivity of any path is always 1. Similarly, the connectivity of stars, any star is 1. If we remove the central vertex, then we get the resultant graph as a disconnected graph. Similarly, the connectivity of tree is always 1. I'm not going in detail uh, with this definition because we have to see the crux of this topic later on. We know the Peterson graph, connectivity of Peterson graph. This is standard graph introduced by the mathematician Peterson, so it is called as Peterson graph. We know that the connectivity of Peterson graph is 3, and complete graph bipartite graph is nothing but the minimum number the less number of vertices in one side we call it is the connectivity of that complete bipartite graph. I'm not going in detail. See, because we have to focus on this main topic, interconnection networks. See, what is mean by interconnection network? See, we have seen just some standard graph, cycle, paths, or stars, Peterson graph. See, if you see any network means it can be anything. If we uh, see, see this network. See, there are some computers, laptop, tab, and they are connected with at some places, right? Means we can do the work from uh, one computer, and we can see it on another computer. Means this is called a LAN connection, right? See, there are some points and they are connected by some links. You see, it is interconnection network, right? Similarly, you can see this network, it contains many processors and links, right? Similarly, this interconnection network. See, these are the interconnection networks. But you can see that every interconnection network we can view as a graph in which processors are vertices of that graph and the links between processors are nothing but just edges of that graph. Means whatever the interconnection network, we can view it as a graph, right? So the study of graph is equivalent to the study of interconnection networks. Just we have seen, right? So my topic was decomposition of graphs. Means we have seen every graph we can view as an interconnection network. So the study of decomposition of graph is just equivalent to the study of decomposition of networks, or you can say interconnection networks. And what are the applications of interconnection decomposition of networks? See, advantages of decomposition of network into disjoint subnetwork has this application. These are very important applications which are network management. We can manage the network well. We can we can improve the performance of the network. We can secure our network. We can reduce the network congestion and controlling network growth. These are the some of the rough application you can say, or important applications of graph decomposition, or you can say decomposition of network. And if we decompose a given network into subnetworks, then two or more processes required in the network we can run simultaneously. One of the subnetworks can run at a given time. Means suppose we have to run two algorithms in a network simultaneously using different subnetworks, we can run them. And so the process can run simultaneously using different subnetworks. Just I have elaborated. Means two different processes we can run simultaneously, or suppose some network interrupts, we can do our work using another subnetwork. So these are the important applications of decomposition of interconnection networks. And just see the formal definition of decomposition of graph. What it means. We decompose the graph means what? See, the decomposition of graph is just a list of edge disjoint subgraphs. Means we have to see the edge disjoint subgraphs H1, H2 up to HK of graph G, such that if we take union of all these graphs is our original graph G. Means what we have to do, just we have to divide our graph into different its subgraphs, and if we see any two subgraphs, there should not be any H common, and if we take union of all these subgraphs, we must get a graph G. Then we say that the graph G is decomposable into the subgraphs H1, H2, HK. G is decomposable into this H region subgraphs, H1, H2, Hk. And suppose all these subgraphs are just isomorphic to a particular graph H for each I, then the decomposition is called an H decomposition of G. See, you can see this definition is very simple, but it has a lot of applications in the graph theory. See, just see the one illustration. Suppose we have a graph G. Suppose this is our graph having 8 vertices and it is connected like this. You can see it looks as a cube, right? And see, in mathematics, in graph theory, the graph is called as Q3. We will see what is meant by Q3 later. Means Q3 just means a hypercube of dimension 3. We are going to see it later, right? See, suppose this is graph H1. This is called as corona graph. You can see its structure is like corona. There is one cycle inside, and we have adjointed pendant vertices to each vertex. So it's structure like corona. So it is called as corona graph, or it is also called as sunlit graph. Sunlit. It likes looks like sun, right? Means circle and the pendant vertices. So it is called as sunlit graph of order 8. And suppose we have another subgraph H2. It is cycle with 4 vertices. You can see that this H1 is a subgraph of graph G. Means we can, if you see these interior vertices of Q3 and these 4 edges, you can see L8 is embedded in Q3. Similarly, C4, this cycle C4 is embedded in G. We can see that this H1 and H2 are subgraphs of Q3, the graph G, and we can see that H1 and H2 does not contain any common vertices. They are not common vertices between H1 and H2. And if we take union of H1 and H2, we get a graph G, right? We get a graph G. So we can say that G is decomposable into H1 and H2. Just a minute. Hmm. Hmm. Now you can see. Hmm. Screen दिसते का था? ते काढलं ते hello?
Yes, yes, sir.
Okay, yeah. See, we can see that the graph G is decomposable into H1 and H2. Definition is very simple. Means we have to look subgraphs of the original graph. There should not be any edge common between them. And if we take union of all the subgraphs, we must get original graph G, right? Let's see. See, this graph G contains a copy of H1. You can see here. Similarly, the graph G contains a copy of C4, right? And see, there are no edges common between H1 and H2. So we say that G is decomposable into H1 and H2. Similarly, suppose again, this is our original graph G, which is Q3, just we have seen. And suppose let's take another graph H, which is a path with 4 vertices. We denote it by P4. You can see that this graph G is decomposable into copies of P4, means copies of H. See, this is one copy of P4. You can see here. This is a path with 4 vertices. Whose edges are just depicted by the red color. See, another copy of P4. You can see blue the graph with blue edges. See, this is a path P4 with green edges, right? And this is fourth copy of P4 with yellow edges. You can see that this graph G is decomposable into 4 copies of the path with 4 vertices. Means we can see that the graph G has P4 decomposition. Just we have seen the definition earlier. See, means suppose if all these subgraphs are isomorphic to particular graph, we say that G has an S decomposition. And suppose there may not the subgraphs may not be isomorphic to each other, then we say that G is decomposable into H1 and H1 is to HK. Means in this first example, we have seen that the graph G is decomposable into 2 non-isomorphic subgraphs H1 and H2, right? And in the second example, we have seen that the graph G is decomposable into 4 copies of P4, means which are isomorphic to each other. Let's see what are the results related to that the definition we have just seen. See, we know that Kn means a complete graph with n vertices, right? And Cn is a cycle with n vertices, right? See, in 1881, there was one mathematician Wallecki who proved that in 1881, for any odd positive integer n greater equal 5, Kn has a Cn decomposition. Means if you take a Kn means a complete graph with n vertices, Cn is a cycle with n vertices. Then he proved that in 1881, for odd n greater equal 5, Kn has a Cn decomposition. Right? And let's see what it means, because since we have considered a general n here, you cannot see imagine it. Let's see just a minute. Hmm. What it means. I just illustrate with graphic. See, let's see what it means. Suppose if you take n is equal to, suppose if you take n is equal to 5. Just a minute. Suppose if you take n is equal to 5, means the result of Wallecki, you can see that K5 has a C5 decomposition. K5 means a complete graph with 5 vertices. Just a minute. Hmm. Hmm. See, we know that what it means a complete graph. We have seen. Huh. See, suppose if we take a complete graph with 5 vertices, you can see that complete graph of 5 vertices means graph containing 5 vertices in which any 2 vertices are adjacent to each other. You can see there are 5 vertices, 0, 1, 2, 3, 4, right? There are 5 vertices, and you can see that any 2 vertices are adjacent means there is a edge between any 2 vertices, right? You can see that this graph K5 has a what value proved for n equal to 5. K5 has a C5 decomposition. Means we can decompose this graph into 2 copies of C5. Can you see the 2 copies of C5 in this graph? Can you see 2 copies of C5? C5 means a circle, right? C5 means circle with 5 vertices. You can see that. See, can you see this cycle in this graph? Yes, see 0, 1, 2, 3, 4. These are adjacent, right? Means you can see this copy here, right? And
Yes.
another copy. Can you see another copy? See, this is just a minute. Hmm. See, I'm just taking vertices. Hmm. I want just selection. Okay, huh. See, now you can see that 0, 1, 2, 3, 4, 5. This is one cycle. You can see this cycle in a complete graphic 5 vertices. And let's see another cycle in which suppose if we join 0 to 2, 2 to 4, 4 to 1, 1 to 3, and 3 to 0. You can see. See, this is also a cycle with 5 vertices. You can see. See, if we move the position of these vertices, you can see it is a cycle with 5 vertices, right? Means you can see that we have 2 copies of C5, and if you take their union, we get the complete graph with 5 vertices, right? Means we can conclude that the K5 has C5 decomposition into 2 copies of C5. Is it right? Did you get what it means? Similarly, we can get a decomposition of K7 into C7. Means you can see that C7, K7 has C7 decomposition. Similarly, K9 has C9 decomposition. But to get the cycles, each time the technique is different, right? And the Walek the proved the result for any odd integer n greater equal 5 means you can prove that Walek given the construction for n equal to 101 also, because 101 is a odd integer. It is he generalized all these results, right? Now, do you get what it mean by the result proved by Walek? Similarly, there is one another famous result, hypercube. See, we have just seen the Q3. Q3 was hypercube of dimension 3. Means this, you can see here Q3, right? Let's see the formal definition of hypercube. Hypercube means what? See, a hypercube of dimension n is denoted by Qn and is nothing but a graph with all n digit binary strings as vertices. Binary strings means uh, the string obtaining from zeros and one only, right? And it contains n digits. Means the Qn has a graph. Qn is a graph with all n digit binary strings are just nothing but the vertices of Qn, and two vertices of Qn are adjacent if and only if they differ at exactly one digit. Means suppose there is difference of only one digit, then we have to join that two vertices, means that two vertices are adjacent. Let's draw what is meant by Q1. See, let's see what is meant by Q1, Q2, Q3, and Q4. Uh, let's generate another graph. See, Q1 means, see, can you tell me how many binary strings of just one, exactly one digit? It is still one digit binary strings. See, there are only two binary strings of one digit. See, 0 and 1. We don't have other choices, right? And you can see that in 0 and 1, there is a difference of exactly one digit. So we have to join them according to definition of hypercube, and we have to call it as Q1. This is our Q1, right? Let's generate what is Q2. In Q2, we have to take vertices. Just change the labels of these vertices. Suppose you can see that there are exactly uh, four binary strings of two digits. We know that, which are 0001, right? Another, can you tell me 10, right? And 11, right? There are exactly four binary strings of two digits. And see, according to the definition of hypercube, we have to join two vertices if they differ at exactly one position. So, according to the definition of hypercube, we can join 00 to 10, because you can see that there is a difference at exactly one position. So, we have to join these two vertices. Similarly, we have to join these two vertices, right? Similarly, we can join these vertices because there is difference of exactly one digit, and we can join these two vertices. And you can see that we cannot join these two vertices, right? Because there is a difference of two digits, right? So first digit and second digit both are different. So we cannot join them by definition of hypercube. And similarly, we cannot join these two vertices, right? Means we can just observe that the hypercube of dimension 2 is just a cycle with four vertices. Let's see what is meant by Q3. Or you can observe that one thing here. See, to obtain a Q2, what we have taken one copy of Q1. See, you can see this as copy of Q1, right? See, this is our Q1, and you can see that this is copy of Q1, right? And this is also a copy of Q1, right? And what we did, we have to get a Q2, we have taken two copies of Q1 and we have joined the corresponding vertices, we got a Q2. Got it? Let's generate hypercube of dimension 3. Means what we have to do? Can you tell me? कोणी सांगू शकतं का? काय असेल hypercube of dimension 3? See, it is also very simple. What we have to do? Uh, See, what we have to do? We have to take one copy of Q2. Just take one copy of Q2. See, this is copy of Q2. We can see that. Means we have to rename the vertices. See, this is copy of Q2, right? 0, 0. Here we will take a 1, 0. काय घेतला होता आपण 0, 1, and here we have taken 1, 1. Right? See, this is a and according to definition of hypercube, we have to join these vertices. See, this is copy of Q2, right? Let's take another copy of Q2 inside this square, and just rename this vertices 0, 0. See, the graph T is one of the important tool to study or graph theory. See, I am constructing graphs in just within 1 minute, right? So while teaching graph theory, you can use this tool graph T software. The name of this software is graph T. See, I have taken another copy of Q2, right? Now what we have to do? We have to just join corresponding vertices. Means if we join 0, 0 to 0, this 0, 0, to this 1, 0, 2, this 1, 0, this 0, 0, 1, 2, this 1, 0, 0, 1, and 1, 1 to this 1, 1. See, this graph is nothing but hypercube of dimension 3. And in the illustration, we have seen that Q3, right? And what we have to do? But it is, since it is Q3, it must contain binary strings of 3 digits, right? So what we have to do? We have to make it as 3 digits. Means if we add 0 in first position of this copy of Q2, we get binary strings of 3 digits. See, we know that there are only 8 possibilities for binary strings of 3 digits. See, we have constructed 4 possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. And in this inside copy, we have to add 1 at first position of each vertex. See, we get all these 8 binary strings having 3 digits. And this copy of this graph is nothing but a hypercube of dimension 3. Right? Means see, while constructing, see, Q1 means just path with 1h, right? 0. This is Q1. While constructing Q2, what we did, we took 2 copies of Q1 and we just joined corresponding vertices. And while constructing Q3, see, we have taken 2 copies of, see, we can take this copy outside like this, right? See, this is one copy of Q2 and this is another copy of Q2, and right, vertices, we get another new graph, and this graph is nothing but hypercube of dimension 3, right? See, now to construct a Q4, what we have to do now? We have to take another copy of this. We have to take another copy of this graph here, right? And if we join corresponding vertices, suppose this is one copy of Q3, and if we construct and if we join the corresponding vertices, we get a new graph which is called as hypercube of dimension 4, right? Means we will get this hypercube of dimension 4. Means we have just seen how to draw this graph Q1, Q2, Q3, and Q4. And see, there is one famous result. The Q4 had C4 decomposition, means we can decompose this Q4 in a cycle with four vertices, as well as Q4 in cycle with 8 vertices, Q4 with cycle with 16 vertices. You can take these just questions for just exercise. The trick is very simple. You can see it. See why I have taken this graph hypercube, because in mathematics, or you can computer science point of view, the graph hypercube is one of the important graph, because if we see any complicated interconnection network, complicated means if you take interconnection network contains many processors and many links, then that interconnection network is homeomorphic to the structure of hypercube, right? So the study of complicated interconnection network is equivalent to the study of hypercube. So the study of decomposition of uh, complicated interconnection network is just the study of the decomposition of equivalent to the study of decomposition of hypercube. So these problems are important. And see, there is one conjecture related to graph decomposition, which is called as Ringel conjecture, because it is read by the mathematician Ringel in 1964, and still this conjecture is unsolved. From this problem is unsolved. See, let's see what is that conjecture. See, let T be any tree with n edges. Means tree means having no cycles. Means cycle free graph, a connected cycle free graph is called as tree. We know it, right? And it contains
Hello, sir.
hello.
Ha.
हा डिस्कनेक्ट झाला
Audible,
होता
audible.
जस्ट मिनिट.
Yes.
हा आता माझी शेवटची स्लाइड होती ही.
Okay, sir.
जस्ट मिनिट. See, we have just I'm see what is the Ringel conjecture. T be any tree with n edges, and then he conjectured that then a complete graph, means if you take a complete graph with 2n+1 vertices, means suppose see, we know that for any n2n+1 is the odd number, right? Then a complete graph with 2n+1 vertices has a T decomposition, and T was any tree with n edges. And see, this is, and we can verify the Ringel conjecture for taking just n equal to 1, n equal to 2, n equal to 3. It is simple task. And it is Ringel raise it for any tree with n edges, and still this conjecture is unsolved.
Background. I got display.
See, I have taken some of the simple problems from the graph decomposition, and we have seen that the topic graph decomposition is very important point of view, the study of interconnection networks. And comparatively, as compared to mathematicians, computer scientists have done very rigorous research in the topic decomposition graphs, right? Okay. On this, with this, I'm stopping here. Thank you. If you have any questions, you can ask. And sorry for technical glitches.
It's okay, sir. Thank you so much, sir, for valuable information regarding recent topic reaction diffusion theory. It will be very helpful for us. Thank you once again, sir. Thank you. Now I would like to call
Thank you.
Pandit Madam for a vote of thanks. And lastly, very big thank you to all participants and listeners of today's program. Pandit Madam, Pandit Madam. Ali sir, Pandit Madam, call Pandit Madam. Hello, Pandit Madam. I like to call Pandit Madam for the vote of thanks. पंडित मॅडम.
Good afternoon, everyone. It's my privilege and honor to propose a vote of thanks on this memorable occasion. First and foremost, I would like to extend my heartfelt gratitude to our chief guests, Dr. R.M. Dhaigude sir and Amol Sonode sir, for gracing us with their presence and sharing their valuable insights. I will also thank for esteemed speaker for their informative and inspiring session. Your words have truly enriched our minds and made this event meaningful ones. A special thanks to our respected principal, vice principal for constant support and encouragement. Also, I thanks to technical support for the Ali sir and the Safe sir. A special, also I grateful thanks for the a big thank to all the participant and audience members. Your enthusiasm and participation made this event lively and engaging. So thanks all of you again.
Jai